Okay, so let's move on to the module then. Tantresh, you can send your doubts from the module. Please go ahead and send any questions and doubts from the module exercises we'll discuss. Okay, so exercise 1, let's start with the discussion of few of the questions. Okay, so Tantresh, exercise 1, question number 2, which you have asked it's a theory question. So I would request you to just go through the explanation of the stress versus strain graph. And its related theory concept from H.C. Verma once. Okay, you'll be able to answer this question. It's not particularly tricky numerical problem. Okay, so just try it out. Okay, just refer to H.C. Verma's explanation of stress versus strain graph in the elasticity chapter, and we'll be able to work that out. Let's come to the 7th question from exercise 1. Let's discuss this one. Okay, so this question, it shows the change in length of a uniform wire caused by the application of stress F at 2 different temperatures. Okay, so you can see that the slope of this line is basically equal to what? It is stress at some point divided by the change in length. The slope is stress divided by delta L. So you can see that Young's modulus of elasticity is equal to what? Stress upon strain. So Young's modulus of elasticity is proportional to the stress. Now you can see that this one, the slope for the second one is greater than the slope for the first one. So that means Young's modulus of elasticity is greater in the second case compared to the first case. Okay, so now you know that what happens with increase in temperature. Okay. With increase in temperature, Young's modulus decreases. So T1 should be greater than T2 because Young's modulus in case of 1 is smaller than Young's modulus in case of 2. So Young's modulus varies with temperature. So again, it is something in the theory part related to this. You can go through this. once again, you can go through the variation of temperature with the variation of modulus of elasticity with respect to temperature in H.C. Verma chapter, and that will also help you to understand all these types of questions, not just this question. Okay, moving on to question number 12. So let's look at this problem. It is rotating. So you have a rod of mass m, length L, and area A with an axis passing at one of the ends. Okay. It's rotating with omega about that. Young's modulus is y, then the increase in length. Okay. So this is a bit of a lengthy problem that involves integration. So I'll just switch to my thing, whiteboard. So exercise 1, question number, this was question number 12. Okay. So in this, what is happening is, if this is the natural state of the rod, it has a length L, area of cross section A, and Young's modulus Y. So in this case, it is under zero stress over here. Okay. But now, when we start rotating it about an axis through one of the ends, perpendicular to the length of the rod, like this, in a horizontal plane, when it starts rotating, it will develop a stress and strain. It will be stressed. Okay, there will be tension. There will be tension. The thing is that the tension will be variable. So this tension is created by centrifugal force. So it is a non-uniform tension. Which creates a non-uniform stress. So therefore, the elongation have to be calculated by integration. So the first step in this is that we will find tension T and stress T by A as a function of position X. If the rod is rotating about this axis, then at a distance X from the axis, at a point like this, we need to find out what the tension is. As a function of X, we need to find out. Okay. So for that, what we'll do is we'll make a free body diagram of this section of the rod. This part of the rod. And that is rotating in angular speed omega, where this distance is X. So its center of mass here will experience a centrifugal force. That centrifugal force is balanced by the tension at this end. So the tension is equal to the centrifugal force. On the section, let's say, of the rod. Okay. So that should be equal to mass of that section into omega square into r of the center of mass. Now the center of mass of that section is at how much distance from the axis of rotation? It's this much. Okay. C is the center of mass of the section PB. So here you can see that the mass of this section PB will be equal to mass per unit length of the rod multiplied by length of that section. And the position of the center of mass with respect to the axis of rotation will be x plus half its length. That becomes x plus L by 2. So from this, you can first step, you can see that the tension, which is the centrifugal force, is equal to m by L into L minus x into omega square into L plus x by 2. So that can be further simplified and written like this. So this is the tension as a function of x position. Okay. So therefore stress, tension per unit area. So stress as a function of x like this. Okay. So the first part of the solution is this, that we have to find the stress as a function of position. It's a variable stress. It's a non-uniform stress. Okay. So this is the first aspect of the solution. Okay. Just make a note of this. Then we'll discuss the second aspect. Okay. The second step from here onwards will be that apply Hooke's law to a differential element to find strain, and then integrate to find delta L for the rod. Okay. So again, this type of thing we have seen before in the case of variable stress, where we have vertically suspended the rod. So the variable tension is acting because of its own weight. The only difference is here, instead of because of weight, the variable tension is happening because of the centrifugal force. So slight difference in the final calculation, but the method is very much the same. So make a note up to this step first, then we'll discuss. Okay, so Tantresh, you've understood this part. Now, the second part. So what we do here is, having understood this variable stress thing, okay, we apply Hooke's law to a small section of the rod. So suppose we consider a small section whose length was dx like this when this was of natural length. So now when this rod is under this variable stress, because it's rotating, the whole rod is stretched out. So it has become of L plus delta L length. Okay. So even this small section, it's got stretched out a little bit. It's under strain. So it has become dx plus delta dx. This is now under stress and strain. Because as we've seen, there is a tension acting. Whether here it was unstressed. Okay. So if this is at a distance x from here, you can see that the stress was something like this. Okay. So the strain, that is delta of dx upon dx, change in length upon natural length, that is equal to stress upon Young's modulus. Okay, because we apply this principle here. So it is so therefore the extension for the element dx, for the differential element in the rod, the extension is equal to, just cross multiply this. Okay. So therefore the extension for the whole rod delta L will come by integrating this delta x. So it will come by integrating this. So just write down these steps and try to work out the integration yourself with the proper limits and all, and you'll see you'll get the answer very easily. Okay, very good, Tantrish. You got this. I'll just complete the calculation for everyone else here. So m omega square by 2 a by L. This is all going to be a constant. L square minus x square dx. Limits are from x equal to 0 to L. So bring the constants outside. Okay. And integrate this term from 0 to L. On this, we have to put the limit 0 to L. So this is the extension that we did. Okay, so that is the conclusion of question number 12. As I said, this was a pretty lengthy question. Moving on to the next doubt. Question number 17 and 18. Same exercise. Okay, so both the questions are based on the concept of pressure difference. So Tantrish, I'll just explain in brief. Okay. Because we've done concepts with similar type of questions in HCV also in the last couple of lectures. So questions 17 and 18, they are both based on the essential idea of capillary rise, but with some variation. So the standard situation of a capillary rise, if we have, okay, then let's just quickly re-understand what happens there. The standard situation of capillary rise, there is a concave meniscus like this because the contact angle is acute, and correspondingly there is a capillary rise of H. So if the contact angle here is theta, symmetrical on both sides, okay, then the center of curvature of the meniscus being here, if this radius of the meniscus is R, okay, and the radius of the capillary is capital R, then we saw that the relation is R is capital R by cos theta of the contact angle, and the capillary height is 2t cos theta divided by rho Rg. But more importantly, the concept behind this is that if you look at the point just below this thing, meniscus, and then compare it with this point here, pressure at the point A will be atmospheric pressure minus 2t by small r. And pressure at the point B will be pressure at A plus rho gh. And pressure at the point B should be equal to atmospheric pressure. So that's how we get from here that equal to this. So H should be equal to 2t upon this, which becomes. So we've gone over this number of times, so I'm sure you're very familiar with this. But now see, this is the standard situation with the assumption that the length of the tube that is there outside is greater than the natural capillary. Okay. But suppose now we push this inside if we make that length as L minus delta L, such that now the length has become less than the natural capillary. So in that situation, what will happen is that the shape of the meniscus will change, as we discussed. So now we have this situation. The height of the capillary itself is such, the length of the capillary above itself is so less that it's not able to accommodate a normal capillary action. So now what happened? The shape of the meniscus changes, so that the new height of the capillary is equal to this new length that we have here. But to accommodate that, the contact angle changes. The contact angle here, it becomes theta prime, let's say. So theta changes to theta prime, so that h changes to h prime. Okay, so now your h prime is 2t cos theta prime divided by rho rg. So the pressure at this point is still equal to atmospheric pressure. So when you compare this equation with this equation, you can see that accordingly the contact angle would have changed from the natural contact angle to this kind of contact angle. So theta prime we can find from here, because this h prime is equal to this new length. Okay. So Tantresh, this is clear. No? This is the concept you will be applying numerically in question number 17. Okay. When you take the standard value of surface tension of water and the contact angle of water with glass is 0, and you calculate the value of h, you will see it will be less than the length of the tube that is provided. So that means the water's contact angle is changing to some new value, and this situation is happening. So hope this is also clear, Tantresh. Okay. Now moving on to question number 18. So question 18 is different in situation, but we'll be using the same formula for pressure difference to understand this. Okay. So instead of a capillary dipped inside a liquid, we have a vertical glass capillary which is open at both the ends and it contains some water. So if L is the length of the water column, then we have to find how much L should be. Okay. So let's understand the question. So again, because it's water, we will go with the standard assumption that the contact angle is 0. But in general, okay, Riti, I'll wait. Okay, so good. So this is done. Now just go through the 18th question, all of you, and try to understand the language of the question. We'll discuss the next question after this, the 18th one. Just go through it, we'll discuss. Okay, so let's find out question number 18. So in question 18, again, what is happening is that you have a capillary this time open from both the ends. It's not dipped inside a surface, but rather both the ends of the capillary are open, and basically you've trapped some liquid inside it. You are able to trap it even though it is placed vertically because of the phenomena of pressure difference created by uh, spherical surface. And the spherical surface is created in the first place because of the whole concept of contact angle. So gravity is acting like this, but this liquid is not flowing out because there is pressure difference created. So if this is the natural contact angle, so here also the natural contact angle will be this. So now we are going to compare 4 points in all. We are going to compare the point just outside the meniscus here, then the point just inside the meniscus here, then this length of this column is L. So the point just inside here, and then just the point outside. Okay. So pressure at the point A is atmospheric pressure. Pressure at the point B will be equal to PA minus 2T by R. So if this radius here, this is R, then this again is PA minus 2T cos theta by capital R. Pressure at the point C will become pressure at the point B plus rho G L. So it will become PA minus 2T cos theta by capital R. That is the pressure at the point B plus rho G L. Okay. So now the pressure at the point D should be pressure at the point C minus 2T by R again. So pressure at the point C plus rho G L, and further minus 2T cos theta by R. So this is the pressure at the point D. So the pressure at the point D should be equal to P naught minus 4T cos theta by R plus rho Gl. And in equilibrium, this should be equal to P naught. Okay, pressure at the point D should be equal to P naught. So for that to happen, the sum of these two terms has to be 0. So you can see that L should become 4T cos theta divided by rho R. Again, because in the example it is water and glass, so take the contact angle as 0. So that cos theta term in the numerator becomes 1. And take the surface tension as surface tension of water standard value, and density as density of water standard value. So this is question number 18. Please make a quick note of this. Now we move on to doubts from exercise 2. So we'll start with question number 3, 4, and 5. We finish writing this down and come to exercise 2 next. Question number 2 and 3. Sorry, question number 3 and 4. So question 3 is basically to do with the formula of elastic potential energy stored in a stressed body. Remember, we had discussed the general formula that energy density or potential energy stored per unit volume, that energy density is half stress into strain. So see if you can make use of that to come to the answer of that. Okay, Diti, we'll discuss that question also. Now coming to the third question. So basically the situation here is that you have an object which is suspended by a wire like this. Now for the wire, the data given to us is that mass m is attached to the lower end. The elongation of the wire is L. Okay. Okay. So we don't know the natural length. So let's assume that the natural length is capital L. So right now the length has become this. Okay. So the elongation is small l and natural length is, so given quantities are small l and m. And nothing else is given. Area of cross section, Young's modulus, all this is not given. So we have to find the potential energy stored in this thing. Okay. So the potential energy is basically, there are two ways of understanding this. Okay. One is that you can think of this as an equivalent spring. That's the easiest way to do. So convert to equivalent spring. Okay. So it is like this now. Okay. So K, remember, is equal to, so I'll just go through the derivation of this also so that you remember this whole concept. So here the idea is that stress upon strain is equal to Young's modulus and the tension is equal to mg. So from this you will see that Ay by capital L into small l, that becomes the tension which is equal to mg. If you look at the equivalent of that over here, you can see that tension is equal to Kx, which is equal to mg. So comparing this equation with this equation, you can see that the equivalent spring constant is Ay by capital L, okay, and the extension is small l. So the potential energy stored in the spring is half kx square. So correspondingly here, the elastic potential energy stored is half Ay by capital L into small l square. Now we have to remove this term Ay by capital L. So that's where this comes in now. So from equation 1, that Ay by capital L can be written as mg by small l. So substitute this in equation 2. You can see that the elastic potential energy stored is half of mg by L into L square. So it's half of mg. So this is the elastic potential energy stored. Just like in this case, okay, the elastic potential energy stored, when you substitute this, it would be half of K, which you can see is mg by x into x square. So like that. So this is the easiest way of doing a question like this. Whether it's a single longitudinal material under stress or it's a combination. If it's a combination, you can convert it to an equivalent combination of springs. Okay, moving on, this was exercise 2, question number 3. Question number 2, part D, right? That is what Diti have asked for. Let's discuss about that. Sorry, part C. Let's discuss that. Okay, so basically, Diti, the concept in this question, okay, I'll come to this. Let's just finish writing that one down. Okay, let's move on to this next question. So question 2C, let's look at this. So in this, what is happening? F is mg by 3. So if the tension in this part is T1, let's say, or TB, let's say, and the tension in this is TA. So you can see that TB is mg by 3 and TA is mg plus TB. So it is 4 mg by 3. Okay. So therefore the stress in the wire A is 4 mg by 3 times pi Ra square, and the stress in the string B is mg by 3 pi Rb square. Now whichever has more stress is likely to break first. Okay. So the one with more stress will break first. So you can see that if Ra is equal to Rb, then obviously B has more A has more stress than B. Okay, then A will break. So this option is correct. Okay. But if, and again similarly, if A is less than B, Ra is less than Rb, then also A will break first. And this is not required. And this is not correct. Achha. If Ra is equal to 2 Rb, then either of them might break first, because in this case, stress in A becomes equal to stress in B if Ra is equal to 2 times Rb. Exactly, then you can see. So this is clear, Diti. Okay, let's move on to question number 4. So next page. Yeah, so question number 4 and 5 quickly we'll discuss. Metal wire of length L, cross-sectional area A, Young's modulus is stretched by a variable force F such that F is always slightly greater than the elastic force. So F is almost equal to but greater than the elastic force. Okay. It is slightly greater than. So when the elongation of the wire is L, the work done by F. So what will happen when the elongation of the wire is L? The elastic potential energy stored is going to be half Ay by capital L, L square. Okay. Now the work done by F is going to be slightly greater than the elastic potential energy stored. Why? Because F is greater than the tension at any given instant. Okay. So elastic potential energy stored is this much, but the work done by F is not this much because it is slightly greater than. So it's not equal to this. And definitely it's not equal to this because it's only slightly greater, not double of. And because work done by F is slightly greater than the potential energy stored, so there will be some heat dissipation also. So this option also becomes wrong. Okay, so Tantresh, hope this question is correct. I mean, it's clear. Now moving on to the 5th question. Okay, make a correction. This should be the answer. Okay. B is incorrect because work done by F is given as Ey into L square by L. So it's double of the potential energy stored, whereas that's not the case. It's only going to be slightly greater. Okay. Let's move on to fifth question. Elastic forces are always conservative. And this is also true. Okay. It is by definition. It is only when the forces become plastic, that is when there is permanent deformity. So plastic forces occur when there is permanent deformation, and those are non-conservative. Whereas elastic forces are by definition conservative, because there is no permanent deformity. So once again, I urge you to go through H.C. Verma theory part very carefully for properties of matter chapter, then these type of questions will not be difficulty for you. Okay, now moving on to question 5 is done. Question 7. Let's complete this quickly. So again, a question to do with capillary action. Capillary tube is dipped in liquid, rises to a height h. The free liquid surface is hemispherical in shape. Okay, so this is again that type of problem only. So what you're doing initially is when you insert the tube in the capillary, in the liquid, this is like this. Okay, so the capillary height is according to this, but more importantly, the contact angle is nearly 0 degrees. Okay. But if you push the capillary further in so that the length of the capillary becomes less than the natural capillary height, then what will happen? It will force the shape of the meniscus to change, like we discussed earlier today. The meniscus will become more flat in comparison, because now whatever is the new value of this length has become the capillary this thing. So that L prime is equal to 2t cos theta prime divided by rho rg. Whereas here you can see h is equal to 2t cos, okay, where this is this. Okay. So comparing these two equations, you can see that h upon L prime is cos 0 divided by cos theta prime. So obviously theta prime becomes greater than 0. It will not come like a fountain. It will not be hemispherical anymore, because theta will now become greater than 0. So the shape of the meniscus will change. Okay, so just make a note of this. Hope this is clear. So again, based on that same concept that we've been doing numerical problems based on also last couple of sessions. Okay, so finish writing up this and take a quick 1 minute breather, because we'll start the next chapter now, simple harmonic motion. No, the liquid will not continuously ooze, na Baba. When you insert the tube, yes, some of the liquid will flow out, okay, but it doesn't ooze out, because it doesn't, for it to ooze out, there has to be a pressure difference created, which will make the liquid continuously ooze out. Okay, Diti, to answer your question exactly, option C would mean if it fills the tube completely, that means the surface should be perfectly flat. It should not be a meniscus. That means the contact angle should become 90 degrees, but it will not become 90 degrees. It will be less than 90, but greater than 0. So there will still be a concave meniscus, in which situation the liquid surface will become perfectly flat when that L prime also becomes 0. When you put the tube perfectly into the liquid such that the surface of liquid is where the open tube is. that's when the meniscus will become perfectly flat. Okay. But until there is some part of the tube outside, there will be some concavity of the meniscus. So the liquid will not completely fill the tube. Hope the explanation is clear why option C is not correct. Okay, C is given, but it's incorrect actually. Okay. Or what they mean by this thing is that, you know, liquid is there up to that height which is equal to the top, and it does not come out. Okay. But how I would interpret the option C is that if it fills the tube, that means it should not be a meniscus. It should not be a concave meniscus. It should be flat. Okay. How they have interpreted the question is that the capillary height itself, H prime is equal to L prime, which I have also written. But that doesn't, in my mind, it does not mean that the liquid completely fills the capillary. No? It doesn't completely fill the tube because there's still a small gap at the top because it's a concave meniscus. That is why I have not marked option C. But probably they have understood the meaning of option C while marking the option as like that. Okay? There's slight ambiguity in the question. It's something that cannot be helped sometimes. Okay. In such type of questions, like, just be a little bit aware and try to answer the question always as per what you can interpret the language best possible. Okay. It's not a numerical answer, so there's always possibility that there is little bit of ambiguity in what the paper setter means by the question and what we have interpreted. Okay. But generally, this should not happen. Okay. It should be, the question should be quite clear, especially in JEE type of papers. Okay, so now what we'll do is we'll move on to the next section of our physics syllabus. Tantresh, to answer your question, heat generation happens when there is permanent deformation, because for heat generation to occur, there has to be non-conservative forces. So that means that has to be plasticity. So the stress has to be beyond the elastic limit. Okay. So just to remind you, there is proportionality limit, then there is elastic limit, then there is yield stress or yield strength, and finally there's breaking stress. So the moment the stress becomes more than the elastic limit, heat generation will occur because the material will show permanent deformation and plasticity. Okay. So just make sure you revise that graph of stress and strain and the explanation of all these limiting values of stress and all from HC Verma only is given in very short, and you don't need more than that. Okay, carefully once, and you should be okay with these type of questions. Okay. Now moving on. So as I said, we will use the rest of today's lecture. The amount of time that we have, we'll use it as a sort of introduction to the next section. It's a very important part of physics for us, which is going to be, overall the section is waves and oscillations. We'll start with oscillations. Now this is again a significant part of our physics syllabus from JEE point of view. It has enough weightage in both JEE mains and advanced, unlike properties of matter and fluids and all, which are very small chapters in that sense. Okay. This is again a bigger section of physics which has quite a bit of weightage. So in this, the first thing we will look at is oscillations. And in that, the chapter that we study in oscillations is called simple harmonic motion. But the concept of oscillations is a bit more general than that. So we'll start with that. So simple harmonic motion, or SHM. So this is the first section that we'll start with. So we start by defining oscillations actually. So we'll see any type of motion in physics, we can, based on whether it is periodic or not, or whether it is repetitive or not, we can first classify into two categories, that is periodic motion, okay, and non-periodic motion. So we'll come to oscillations, but first of all, let's understand that based on this property of the time dependence of motion, we can classify it into two categories, periodic motion and non-periodic motion. Any motion which has a fixed time period, any repetitive or cyclical motion. Yeah. Okay. So any repetitive or cyclical motion which occurs with a definite cyclic time period, which repeats in a definite cycle or time period is called periodic motion, whereas non-periodic motion is non-repetitive. So anything that is non-repetitive. So for example, projectile motion is not a repetitive motion. Okay. Or anything of that type, free fall research motion. Okay. Whereas uniform circular motion is an example of a periodic motion. Okay. Then oscillations of a pendulum, an example of a periodic motion. Okay. Then, for example, orbital motion of planets, okay, or an elastic ball bouncing repeatedly off a floor elastically. If there's no loss of energy because the collisions are elastic, then it's a perpetual motion. It goes on and on forever, keeps bouncing forever, and keeps repeating itself exactly. So these are all examples of periodic motion. Just make a quick note of this, then we will understand the next thing, that is oscillations. So we'll understand that oscillation is a special category of periodic motion. So some of the examples which I've shown here on the left hand side are not only periodic, but they are also oscillations. Where some of the examples are going to be periodic, but they are not going to be oscillatory in nature. Okay, so next up, let's understand further that periodic motion itself can be broken into two categories: oscillations and non-oscillations. Now, this will be very easy to understand with the examples. Okay. Oscillation by definition is a to and fro motion with definite amplitude and time period. The most important thing, the to and fro motion is about a mean position. So example of an oscillation is a pendulum or a spring mass system continuously oscillating. Whereas in non-oscillation, there is periodic motion such that there is no mean position. Example, uniform circular motion. There is no mean period, mean position. It's just a continuous motion that is happening repeatedly. Okay, now let's discuss a little bit more in detail about oscillations. So in order for a system to oscillate, there should be a defined mean position. And physics wise, what the meaning of this term mean position means is that it is a stable equilibrium position. Okay, so that means that the net force at the mean position should be equal to 0. Okay. And there should be restorative force. That means force pointing towards the mean position. When displaced away from the mean position. An example of that is, for example, a spring mass system. It has this property and therefore it is capable of oscillating. That if we have a block placed on a smooth surface, the surface should not have friction so that the motion is perpetual. It should forever oscillate with a definite time period and amplitude. So this is a spring and this is a smooth surface. Now this is natural length. Then you can see that at this position, the acceleration of the block will be 0. So this is the mean position. But from the mean position, we take the block either direction. Here the spring gets compressed. So it will push the block in this direction with a tension equal to kx. So it will have an acceleration which is opposite to the direction of displacement. Okay. Or we take it to the other side. The displacement is towards the right. Then we'll see the spring has got extended. Okay. So this has now become L plus X. So it will apply a tension in this direction. So it will now have an acceleration in this direction, whereas the displacement was in this direction. So in both cases, you can see, so on either side of equilibrium, or mean position, there is a restorative force. That is, the net force acts towards mean position. It tries to restore it back to the mean position. So it is called restorative force. Okay. So that is the necessary condition for oscillation. And the other thing is, the system should have a periodic to and fro motion. That is, it keeps going one direction, then the other direction. So it should have a definite periodic to and fro motion. With definite amplitude and time period. So what this translates to is that it implies that there should be no non-conservative force, no dissipation of energy should occur. So friction, viscosity, these type of things should not be there. Okay, so this is what we require for a system to be able to oscillate. आदेश जी, मैं आफ्टरनून में ना आपके पास एक डेस्कटॉप छोड़ के गया था और एक हार्ड ड्राइव भी. हाँ, डेटा बैकअप डेल वाले. अच्छा अच्छा. ठीक. हाँ हाँ, चलेगा, मैं कर लेता हूँ. ठीक है ठीक है. कितना टाइम लगेगा रफली हार्ड ड्राइव पे? ठीक है, तो कल सुबह मैं कर लेता हूँ. हाँ. और ये डेस्कटॉप का कुछ अपडेट? अच्छा, चेक नहीं हुआ है. ठीक है. अच्छा, होता है तो आप मुझे एक अपडेट दे देना. Okay, Ansh, to answer your question, UCM, uniform circular motion, is non-oscillatory because there is no mean position. Okay, there is no point during the motion at which the net force is zero. Continuously centripetal force is acting. Okay, and continuously the speed is constant. It does not have an amplitude with respect to mean position about which it is going to and fro. Have you understood now, Ansh? And Kshitij, yes, to answer your question, there will be a mean position in case of pendulum also, and that is the lowest position. That is the equilibrium position. So when the pendulum is at that vertical lowest position, if you leave it at that position, it will continue then, because there's no net force. But if you give it some energy, then it will oscillate back and forth with respect to that position. Just like the spring mass system, if you leave it at the position at which the spring is relaxed, nothing will happen. It will remain there because it's an equilibrium position. It's only if you give it some energy, if you give it an impulse or some energy or some potential energy or whatever, it will then keep oscillating with respect to that mean position. So that is the type of motion. Yes, in uniform circular motion, there is always a net force equal to mv square by r. Visualize the free body diagram at any point of time. Okay. It's a continuous motion at uniform speed, and continuously the body is turning. So there is centripetal force acting on it. Okay, so we will continue from this point onwards in the next lecture, because now we have to get into the technical definition of simple harmonic motion and all that. So I think we have one more lecture this week, so we will be able to cover quite a significant portion of simple harmonic motion in that. Yeah, Tantrish, about your question for practice of advanced level questions, your module is an excellent this thing. It is an excellent source of questions for JEE Advanced as well as JEE Mains level. HC Verma also, the last few questions of every chapter, the last 20% or so of the questions will give you good practice at advanced level. Though the pattern of the questions is subjective, but the level of the questions is advanced level. Whereas in your module, you have the same pattern questions also as the JEE Advanced. And if you still want to do some additional practice, then there is DC Pandey of Arihant publication. That's an excellent series of books.
Sir, is module enough?
DC Pandey, there is also Cengage, but DC Pandey is excellent at this stage.
Excuse
okay,
me,
so
sir.
that's it for today's session, people. Wish you all the best. Have a nice day.
Excuse me, sir. Sir.